let's see. So I'll go over this. I kind of added a bullet that's nothing to do with my model and more kind of meta talk. As I'll go in my background, I'm actually, my daughter 2 years ago did have a bone marrow transplant. So I have a lot of sort of personal vested interest in this exact topic. And just, you know, what I actually needed wasn't available. And for me, it's, you know, worth calling out that this by itself doesn't solve that, doesn't fill the need that I saw. And that's fine. You know, this may not be for parents and patients in particular, but I want to kind of talk a little about that if we have time. And if the host, you know, doesn't mind me going on about that. Obviously, I don't know you guys' use case and what you're trying to accomplish, so I can only talk so much, but I can give a little bit about what I see as the need and maybe ways we can get there. Unlike, I guess, every other team, I'm not yet working in the machine learning industry. I'm a firmware engineer, and I've just kind of self-taught this maybe 5 years ago in terms of when I entered Kaggle competitions, maybe 3, I forget. But I have done well. I also got 3rd place in this auto machine learning Grand Prix, and relevant for that, that was actually a synthetic data competition. So I was kind of half expecting things like feature engineering to not necessarily work. That there may have been some advantages in my approach, given that it was synthetic data. Let's see. I think it's also worth mentioning, like, you know, my modeling approach and how I did this. I took this. There was a lot of sort of exploration that I did. It wasn't where, because I was not at the top of the public leaderboard, and a lot of people at the top were saying they were seeing pretty good CV to public leaderboard. I kind of knew I was in a sense behind in the competition. I ended up so I was just looking for the trick, and I got 5th place because in the end I found, you know, the kind of try A versus B, which I'd thought of in the past but never tried, maybe like 11 days before the competition was over. So as such, my models were not as polished. You know, I think 1st and 2nd in particular, their single models, you know, were at least on the edge of beating 3rd, 4th place, and definitely beat mine. You know, even with single models, they could have done that, right? So I did a lot of things I'm very proud of, but, you know, one of the things that will win a 3-month competition is getting really good individual models, and I didn't do that to the level 1st and 2nd did, and I think that's worth kind of calling out. But what I did do, as what I did in auto machine learning, is I took a lot of public notebooks and hand-tuned light GBM in particular, which I'm at least very familiar with and can tune very quickly, and hand-tuned one of the public models in particular, the TAB-M. And then I also ran AutoGlue on, so I got this, you know, what ended up really, in a sense, being hundreds and thousands of models because of the target proliferation, and then sort of merged them back down. Different from, I think, each of the other teams, I did merge in, or at least most of the other teams, I did merge in ones that were trying to predict custom targets, in addition to the A plus B, you know, the classifier and regressor combination. I had a formula for that, but I also merged in a little, I saw some benefit in also merging in something that was trying to predict against single labels, and I merged them back at the end. I did have a few small feature tweaks, but the main important feature was just the target, figuring out how to do the target. Training time, you know, if you look at what all of them were that were thrown into this kind of blender ensemble method, it would be large, but if it was only the final models, the training time would be at least a little bit more reasonable, even when it's running AutoGlue on. Oh, and I also apologize. Some of this is not as polished as I would like on the slideshow. I'm on vacation, and even for the last 2 weeks, I didn't have a lot of time to throw this together. This is all a little bit better in my write-up, and I'll try to talk to everything, but I may not have it all captured in bullet points. So I had the classifier, you know, predicting EFS. was what I'm calling A in this formula here, and then B was the ranking of the EFS time. But I also did something very different. So I had a custom variant of predicting the EFS label because I noticed that there was surprisingly low overlap if you found the exact point where there was the least overlap between EFS 0 and EFS 1 by EFS time, like where essentially you find this kind of cut point where as few EFS equals 1 are on one side of that, and as few EFS equals 0 are on the other side of that exact EFS time. It ended up being this like, 13.32 months or something like that. I forget what the number was. It's in my write-up, but there was only about 2% that were on the wrong side. And I considered 2% to be, like, well, what if that's noise and I'm actually better off pretending that I'm just trying to predict whether a patient will reach this 13.324 months mark. So my custom classifier is actually predicting a custom variant of that. And I also said, for the censored ones that were before 13.24, like the 200 that didn't reach that mark, I said, let's, instead of using them as one or the other, I'm just going to ignore it. I'm just going to drop those ones from my classifier for training. So I'll just ignore the ones that were censored crazy early. Something weird happened, let's ignore that, and only use the others. And then for time, I just only looked at the ones that were under this artificial cutoff point, and were actually, an event happened. So my A and B was a little bit custom because of limited time. By the time I was trying this thing, I never had a chance to go back and find out, would I have been better off doing both methods, only one method or the other, in terms of using a true EFS versus using this custom label? I didn't have a chance to figure out which was actually better. This was just the one I ended up using, and it worked well. But it may actually not be better. I didn't have the chance to check. Oh, sorry. The other thing I did before I got there is I did this large search where I was, using a formula to sort of modify my single regressor trained on all the data to train a single risk score. One of the things that worked really well was having sample weights. Again, this works less well than splitting the targets, but it is somewhat helpful as a supplemental. And one of the things that worked really well was having a sample weight in the 30 to 35% range, depending on like 30 to 40% range for the EFS 0 samples, so that you were mostly looking at the ones that mattered the most, but you were getting just enough kind of pull for the ones that were 0 that the trees were able to make good splits. And I think that was where that's where they had so much trouble, as shown in one of the other graphs of predicting. It just helps it a lot if it can figure out that this group means this thing. And that was hard to do both for ranking and at the same time, what about these ones that you need to always rank lower? Became a little bit tricky. Let's see. I did do a couple features. They were not super important. They definitely seemed to help a little, but not a ton. There was a recalculating HLA sums because of synthetic data. But one thing is that in that one, I noticed that they couldn't replicate the NMLP feature properly, because it's synthetic data maybe. So I made both. I was like, well, that could help, but let's also keep the original one because that was a highly predictive feature compared to most of the HLA. Most HLA ones didn't seem to be very, very predictive in the first place. For gradient boosters, I never got to trying it, but the winner did, the one-hot encoding, numerical as categorical. I've done that in the past before. I just didn't get to it in this one. And the nice thing for gradient boosted trees is because of how they work, it's generally best to just add and not subtract anything. So, the first place solution was a great approach for that. For neural nets, however, and even the first place solution, I'd be curious if paring it down a little bit would help neural nets, because sometimes neural nets, if you add too many features, it is a little bit influenced by random features. So non-predictive features can sometimes be helpful to remove for neural nets. So I did remove just the HLA6 and HLA8 sums because logically they should be pretty encapsulated in the HLA10 and the individual ones. So the neural net can figure it out on its own. You don't need to sum every single combination of sum. For neural nets, it was how it was done in some notebooks, and I left it and didn't have a lot of time to go back, and I just kind of forced all but two as categorical. That I did also is it's a pretty quick way to have diversity between the main models, because the GBDTs will usually do much better, and the neural nets. Another thing I did when that was more because I was worried about my delta between public leaderboard and training data, but I think is also just a good approach, is I slightly rounded the numerical features. One of them was like the age of the donor, and obviously that's not going to be very sensitive to outcome. You know, you don't really care if they were 23 in 1 month versus 23 in 3 months. There's not going to be relevant data there. So so I rounded that, I think, to the nearest 2 years. And then for the age of the patient, there is going to be quite a bit of difference potentially, but it's still not going to be at the level of, you know, 23 years, 2 months and 4 days versus 23 years, 2 months and 7 days, right? So I rounded to 0.1, which would be roughly rounding to the month. And I actually ended up using both the rounded and not rounded, but I mostly, from the point that I tried that, used mostly the rounded version, and that seemed to help very slightly. And then sometimes since I included some public notebooks, sometimes the diversity of having them with features, even if those features are kind of noisy and probably not helpful, can be a little bit of help just by injecting diversity. I kind of already talked a little bit of this. You know, I used a lot of training methods. I used a large ensemble. I use this greedy ensemble selection where you basically add one model and try to improve the score. Then you pick the model that adds best to that one and just keep going until you don't see improvement. I do that also with the validation thing. So instead of stopping when training is not improving, I stop when validation is not improving, well, optimizing the training set, not the validation set. So that it means that, you know, what originally I did, you know, this 1,700 different target variations, but then I ended up only using about 6, I believe, of those target variations based on this ensemble method. So then when running those 6 methods on a whole bunch of different things, plus running the A and B, that's when I then ensembled these all. That's how it's very similar to AutoGluon's built-in, although I was not using my own custom version of that. So that's how I'm using what ends up being, you know, dozens or hundreds of, I think it was like 46 models that made the final solution, plus a whole bunch that did not make the final solution, and I ensembled them all. I saw this very tiny degradation when I removed all the ones that weren't in my final, because of just how the algorithm works even slightly better when you truly have all of them, but it was not a relevant difference. Cat Boost was really good because of the categorical data, but I'm not as good at tuning it, so I didn't ever really hand tune it. I just used some public notebooks, and AutoGluon has some good Cat Boost settings, so AutoGluon really did the lion's share of the Cat Boost portion of it, although I did a tiny bit of hand tuning of it, but almost none. Tab-in I hand tuned, but I don't know how much. I definitely feel like it was better, but I wasn't able to get this huge improvement there, but some. And then the ODST, although I spent time on it, I wasn't able to improve, so I just used it kind of as is, but with a new seed to reduce its overfitting of the public leaderboard. So while my models were not, you know, quite at the level state of the art of the first place, a couple things that I did that I really like to do, and I don't think I've ever seen it not work where it made sense, is leaving things as logits if they were that in the first place, before converting them to probabilities after ensembling. you know, and I also did for the ranking EFS time, I converted that to as if it was a logit. I ended up I ended up making it from like 0.03 to 0.97 instead of 0 to 1 ranking. And then I took the logit of that 0.3 to 0.97. And then I trained the regressor to predict the logit value instead of predicting the raw probability or the raw ranking. So it was a way of, I think another team also saw it better when they did a logistic or an exponential, I forget. Anyway, I believe it was similar to them, just from a different approach. But because I did it that way, I also found that for the regressor as well, leaving it as logits during ensembling was better and only transform at the end. Then because it was logits, I found certain post-processing was really effective. And I didn't have a time to really write this into here, but I believe, well, oh, I did a little bit. Yeah, I believe the big difference here. So I think I did a conservative 1.5 because it wasn't working on public, but it ended up working really well on private and training, which was more data. So I suspect that I could have actually gone a little bit higher. I didn't have a time to go back and test it, but I suspect a higher value than what I did would be even better. And I wouldn't be shocked if it would also improve like second place team to do the post-processing, even though they also saw some post-processing do worse on public leaderboards, so they didn't do it. But I think that may have just been noise on the public. What I found, what I speculate is, I think there could be also this, because of the survival GAN, because it's synthetic data, there's some reasons why perhaps the split works especially well, and the post-processing might be related to that. But I actually think it's the concordance index, not because of how the concordance index does, you know, censoring or comparisons, but really the fact that the concordance index is a relative and not, you know, an absolute. What that means and you're just looking at risk, specifically the risk score portion of the concordance index. You know, you're comparing just these relative values. They don't have an absolute meaning. And what I speculate is the reason for post-processing is actually because if you already know that all of the models, let's say you're 200 most risky out of 10,000, you're 1% most risky, data points. Well, you no longer care whether those 200, you've already ranked them above the other, you know, 9,900, 9,800. So you really, you actually still get a small amount of benefit if you then essentially say, well, what about within this 200? Which one should I call the highest risk and which one should I call the second highest risk? It's no longer that, hey, A is 99% likely to beat the ones that we're ranking ahead of it, and 2 is only 94% likely to beat all those other ones. Well, that doesn't matter because you already said it's probably going to beat them. Now all you care about is, will it beat the other 199 within this little group? You can think of it that way, right? And so I speculate that further emphasizing these logits helps basically zoom in on a kind of a local optimized rank. I never had a chance to do other experiments on that, so it's kind of, I'd call it just a speculation at this point. But I did two different things. I believe that multiplying the logit by a larger value, you know, when it's probably EFS 0, now you're saying there's less and less importance I'm going to put on its EFS 1 ranking. So therefore, with the least risky ones, I'm paying more attention to what's the slight chance that I'm just wrong and it's not an EFS 0, because that's all that's going to matter for your ranking score. And the other way, if it's an EFS 1, I'm emphasizing both of them. And that just means that now I'm just essentially looking at what is the chance that this one beats another one. So you're kind of, again, you're emphasizing what matters for that section. And then I also had this little move away from 0, the EFS probability. which again, I speculate helps locally optimize the middle of the range, where you're just, hey, I'm going to pretend to be just a little more confident than I really am, which will probably slightly help me figure out, because probably the classifier has a little bit more signal than the regressor for these unknown data points, the ones that you're just not very good at figuring out. So that was kind of what I did there. I suspect that that would see benefit even in first and second place. That's why I'm kind of spending a little more time talking about it, but I don't know that. I didn't have a chance to run that experiment. I found that cat boost was most important for EFS classifier prediction, and light GBM worked best for me, at least, for the regressor prediction. I did something that probably was not nearly as good as what first place did, where they put everything into the regressor. I used only the half of the data, but I did have the rest of the data in with sample weight equals 0, which weirdly made more difference than I expected. I think it was something about how it does the grouping, even though it doesn't affect the weights given, it somehow affects the grouping, at least with the regression, not with regression, with the regularization settings that I had. For the simple model, I found that this really simple pairing of cat boost and tab-in for classification and light GBM and cat boost for regression worked really well with this, like, kind of doubling the logits at the end to really emphasize this local confidence. So for me, it got a 69812, which was within, which would have been like 6th or 7th place, and it was very close to my full model's score. Let me ask real briefly, if it's fine for me to, I'll just go just real briefly on some kind of off topic, off the main topic stuff. If that's fine.
If that's okay with the hosting team.
Yeah, that works for me.
Okay. So for me, the big question where I was literally looking to find out whether I can find data, because obviously I am an accomplished data scientist and know what I'm doing, was, hey, can I figure out whether my daughter doing a CAR T and then hoping it works, and it often does not. It's only got about a 50% success rate. But the other 50% is almost always relapse. There's very little risk for a kid, at least, of not surviving, of anything happening besides relapse. And if it works, there's very little sort of side effects. You're not doing anything too harsh on the body. There is a window of time that's dangerous and that is hard on the body, but it's small and it's pretty well contained with modern medicine currently. But it's super new. There's not a lot of data. Even if we had great models, the models would not be very confident. But that's what I wanted. I wanted the most confident we can get instead of this pure guesswork. Or the other approach is for bone marrow transplants, and with leukemia in particular, it's actually very critical that there's no, and I'm sure the hosting team is aware of this, but it's very critical that there's no sign of leukemia. And the way I was told, my understanding of this is essentially one of the dangers is it takes a really long time for the new immune system to really mature. And the goal, what you need, is for the new immune system to mature before any leukemia that may have still been around is able to exponentially grow. So CAR T is the best a bridge to transplant. So we were doing CAR T either way, but we didn't know whether to just immediately do a bone marrow transplant no matter what, or try to see if the CAR T would take. And bone marrow transplant has a much higher success rate of more like 70% for children. I think it was around that level, and probably a little better because the statistics usually lag the medicine because they're such long 5-year studies. And but on the other hand, a lot of the failures with bone marrow transplant are more serious. You know, relapse is actually a much smaller percentage, and there's much higher chance of passing away, and there's also a lot more long-term side effects. You know, simply going through the radiation means you have a small but a slightly higher chance of unrelated cancers or other complications. But for me, it was really not even which one is better, but it was which one impacts the other one. You know, you could do a bone marrow transplant, and then if that doesn't work, and you just relapse, well, you could just do CAR T. You know, if you could do CAR T and then wait 2 years, and when you finally relapse, you can do bone marrow transplant. But it's not as simple as that, because if you've relapsed, you have the worry of, can I get it back under control again in the first place? If you use CAR T into bone marrow transplant, well, maybe the fact that you've exposed it to CAR T the first time means you can't use the same CAR T the second time, and it's less likely to work. So it's also really hard to know, and would even be hard to model, even if we had the right models. The really specific of, I did X and now I'm trying to do Y, or how did that affect my chance of Y? But there's still, there's still some level of extrapolation you can do if you have a sufficient data. And even if you have insufficient data, a little extrapolation, just not much. So my, kind of question really is what are we trying? What are you trying to solve? Who is this for? Is this for, doctors and researchers? Is this for patients? And almost regardless of that question, I'll just kind of, since I'm just writing the slides, I'll just give my take is that you need not simply a risk score, but you really need the set of models that almost is like a flow chart, and then you do really the same as this A and B, right? Really the flow chart for this solution was, does an event happen? Yes or no? If no, we're done. We know our risk score, it's super low. If yes, then it was like, okay, and how quickly does it happen? That's our risk score. But instead, we can have, what we really want is what's our chance of hitting no? Where you're like, okay, how relapse happened, but that doesn't mean we've lost. Now we've got to try a new thing. If we say one more relapse and throw into this, some other model, that a leukemia group has made for trying experimental drugs, what are our chances? And, I feel like there's this theoretical ability for each kind of, for a group of owners to start publishing open source models, or, at least open models that do a small piece of this. A CAR T group can be like, well, our model's not super accurate. It's only so great because we only have so much data, but here is the model, and you can feed data into it, and you can say, what if they've done a CAR T therapy before as a part of bone marrow transplant? That can be one of the features of the model. So another thing that I think is really difficult, and I really noticed when looking at the data, is it's really hard to get all the features that would help this meta model into your model, and I'm not sure if they're all there today or not. But then the bigger one, I think, is that target, that EFS equal 1 or 0. Can we get something that's not simply an event happened, but a lot more stratified on, okay, at this point, chronic graft versus host happened. At this point, relapse happened versus survival, they passed away, all these other possibilities. And of course, if we can then model confidence intervals, that'll be really helpful for patients and doctors in terms of if they're trying to weigh two very different plans of attack, knowing that, okay, obviously the CAR T model, its confidence is all over the place. It could be, it doesn't really know, it just has at least a speculation for how long, because there's so much less data than for bone marrow transplant. I think everyone's already mentioned the synthetic data. I'll just, add, there's, it makes it harder to figure out what the best model would be. It definitely allows you to do a good model. It's possible that, you know, some of the people here could have made even more amazing models with access to real data. The metric, you know, I have a bit of a concern with the concordance index, because even when you split into this classifier and regressor, you still are basically forced to combine it into one at the end. And it's this ranking where local optimization matters, and that maybe isn't really the most important thing. You know, it's possible that actually training, that actually having a metric of the EFS classifier and a metric of ranking, you know, when it'll happen for individual events is a better, you know, like actually literally breaking up, that might work better for sort of real world scenarios. And as I mentioned, you know, the target columns having more granularity of what's really happening, again, helps with this sort of that concept. And, you know, so I just kind of briefly, you know, obviously there's, well, if no adverse outcomes happened within certain time range versus, you know, not surviving versus relapse versus an unusual relapse, right? Where, you know, you can get a mutation, you can get 20 years later an unrelated cancer or whatever. And then I'm not really sure what the other possibilities are. I know there's chronic graft versus host, and I think there might be other things that are, you know, a form of rejecting the bone marrow transplant that would also need to be considered an event. But that's all I have. I just kind of wanted to highlight that because that's near to my heart. I hope you guys, you know, I love that this competition happened, and I hope you guys are able to kind of further find ways to help the patient community.